Like for example, you might remember pre and post index instructions, which do memory access and which do manipulate the value of a register in the same instruction, right? And there are instructions where the program counter can be a destination, which can change the program counter of that key, which sort of performs a branch-like function. So now you are in some sense combining arithmetic and branch into one. And that's why I said, ARM is not entirely or canonically RISC, but it's considered more RISC than CISC. That's it. Now, every instruction in ARM can be conditionally executed, ARM version 3. This again is a very significant departure from what you got seen in CG3207 if you have taken that module. There, only branch instructions use conditions, right? Whereas in reality in ARM version 3, every instruction can be conditionally executed. Okay, and without the so-called IT suffix. IT suffix is something that is required only in the newer versions like COM2. Whereas in the older versions, you can have an instruction like add EQ without any IT EQ before it. So let's say if you have an instruction add EQ R1, R2, R3, you will add R2 and R3 and store it in R1 only if the condition EQ is true. And the condition EQ is said to be true when zero flag is 1. When zero flag is 1, the condition EQ is true. And you can see here, EQ, it checks for whether zero flag is true. So when 0 is 1, the condition EQ is said to be true. Yeah. And so on. There are 16 different condition codes, which is exactly the same as what you have seen in EE or CG3208, which is common for all ARM processors irrespective of version. Now, the condition is encoded as a 4-bit value because there are 16 possible conditions. And you can see these 16 are in fact 8 pairs. So one positive condition and one negative condition. So EQ has its opposite NP, which is, well, the logical complement of the condition for EQ, which is the complement of Z, which is Z bar. And similarly, CSHS, C, LO, C bar, and so on and so forth. These mnemonics make sense only for sub S or CMP instructions. Okay, so when you are using it in the context of CMP or sub S instruction, you can see that these mnemonics will make sense. And the connection between these mnemonics or conditions and flags is very interesting. If you can understand the connection between the two, your knowledge of computer arithmetic will be a lot better. Signed, unsigned, etc. etc. Okay, so homework exercise for you. Try and make sense of each and every logical condition mentioned here. So for example, unsigned higher, why is it Z bar C? And signed less than, why is it N XOR B? Try to make sense of it. Okay, it's not very trivial, but if you can, and you should, then you will understand things a lot better. Now, what are these conditions? Conditions are essentially suffixes to check for a certain situation of a flag register. And we all know for ARM there are 4 flag registers. N, negative, 0, 0 is Z, 0, negative, 0, carry and overflow. Okay, we will look at these things in a bit more detail in the next chapter, which is on arithmetic for computers. Okay, how we can derive circuitry to generate all these flags, etc. etc. But who sets these flags? Any instruction with a suffix S. So for example, if you write something like sub S, then NS and CV flags will be affected. So only instructions with suffix S, and those instructions whose sole purpose is to change flags, like CMP, CMN, TST, TEQ. Okay, they are somewhat similar to sub-S, RDS, then TST is AND-S, and TEQ is XORS, EORS. It's not exactly the same. The difference is that instructions such as CMP, CMN, TST, TEQ do not change any destination register other than flags. Whereas an instruction like sub-S will change a destination. Like for example, if I write sub-S R1, R2, R3, you will do R2 minus R3 and store it in R1 and also affect NSHCV flags based on the computation, based on the result.
So RISC-V doesn't have CMP,
RISC-V doesn't. RISC-V in fact does not even have a flag register. It does not have NSHCV equivalent flags. So the result of some comparison etc. are stored in another general purpose register, not in a flag register, which is more in compliance with RISC philosophy that one instruction affects only one register. Whereas in some sense, in ARM, an instruction like this affects R1 as well as flag registers, which goes a bit against RISC philosophy. Now let's look at the format of data processing instructions. They have the format. Okay, first 4 bits, most significant 4 bits have the condition, and then you have opcode in bit 27, 26, which shows which category of instruction it is. Opcode is 00 for data processing, 01 for memory, 10 for branch, and 11 for now is invalid. Then func field gives more details about the operation. Like for example, what exactly is the arithmetic operation performed, whether the flags are supposed to be saved or not, that is whether there is an S suffix or not, and whether the second source operand is an immediate or register. So all those go into func field, which we will see later. Then Rn is the first source operand. Rd is the destination operand. And then there is SRC2, which has a format which varies depending on the exact category within the data processing instruction. So anyway, a typical data processing instruction has a format in assembly language OP, RD, Rn, SRC2, where RD is the destination register, Rn is the first source register, SRC2 is the second source, which could be a register or immediate with possible modifications. Okay, so Rn is the first source register. Even though in assembly language it is written second, in machine language or machine code it appears ahead of other operands. RD is the destination, so in machine code in fact these two are sort of swapped. So here is your RD. SRC2 has a format which we will look at in more detail in subsequent slides. CUND specifies the condition for execution, which is one of these 16 possibilities. By the way, only 15 possibilities are valid. The last possibility, 1111, is invalid. Because if an instruction is supposed to execute unconditionally, like for example, AND R1, R2, R3 has no condition involved, right? It is executed and R1 is modified, AND R1, R2, R3. So that has an implicit condition always. Now you see all these conditions are complements of each other or opposites of each other. So the opposite of always should be never, which doesn't make sense, and that's why the 15th one doesn't exist. Sorry, 16th one doesn't exist. Only 15 valid conditions are there. Yeah, vast majority of the instructions are likely to be unconditional, and that's why you have 1110, and 1110 in hexadecimal is E, and that's why vast majority of our instructions will start with E. already mentioned, it is 00 for data processing, 01 for memory, 10 for branch. Func field has basically 3 subfields. Bit 25 is an I bit which tells whether the second operand is an immediate or a register. CMD is a 4-bit field which specifies which arithmetic or logical operation it is. Like for example, whether it's addition, subtraction, add, sub, XOR, and etc. etc. So that distinction is made using this 4-bit field. Then the suffix S is bit number 20. So if the instruction has something like add S, that suffix S, this bit will be 1, otherwise it will be 0. Yep. And CMD is 0100 for add, 0010 for sub, and so on. You can see page A39 of ARM instruction manual for a complete CMD code list. I bit is equal to 0 means the SRC field, SRC2 field is interpreted as a register type. Whereas if I bit is 1, it's interpreted as immediate type. And then S bit is the suffix bit. Now SRC2 can be 3 different possibilities. It can be an immediate with an optional rotation, or it can be a register with a shift which is specified as an immediate, or it can be a register with a shift specified in a register. So there are 3 possibilities for operand 2 or source 2. You can see here, these are the 3 possibilities. So you have an immediate 8 with an optional rotation for immediate type. Okay, we will see that in more detail in subsequent slides. Then there is register shifted immediate, which is simply called register, where the second operand is whatever you have in RM shifted by an amount specified in SHAMT5, and the type of shift is specified as SH. And this bit is required to be 0. Now the third variant is register shifted register, where the second operand is this register shifted by an amount specified in this register, and the type of shift is specified here. Okay, it will be clearer once we see some examples. Now, the most difficult to understand one is the first one, which is immediate type. In immediate type, SRC2, the 12-bit field, is encoded as an 8-bit immediate with a rotation. Now, you can specify a 32-bit constant here. So, for example, I can specify something like, say, add R1, R2, let's say AB 000000. Now, okay, with a hashtag, and that is to show that it's an immediate. So you can specify the second operand, which can be a 32-bit value, provided it can be encoded using an 8-bit value with an even rotation. So the 32-bit constant is the immediate 8, rotate right the amount given by ROT into 2. Now that can be quite confusing when I just say like this, but will be much clearer when we see an example. So let's look at the encoding for sub R2, R3, hex FF0. You can see this instruction is an unconditional instruction. So the COND field is 1110, or in hexadecimal it will be E. And then OP is 00 because we are looking at data processing type instructions. And then since the second source operand is an immediate type, not a register type, your I bit is 1. Okay, if it is a register type, it would have been 0. Right now it's immediate type, so it's 1. the operation to be performed is sub, which is 0010. So the CMD corresponding to that is 0010. And it is a sub instruction, not a sub as instruction. So bit number 20 is 0. Now your RN is R3. So this field is 00113. Then RD is R2. So bits 15 down to 12 is 2. Now comes encoding of this constant. So this constant is encoded as an 8-bit value with an even rotation. So here hex FF0 is in fact hex FF, which is an 8-bit quantity shifted left by 4 positions. Why 4 positions? 1 hex digit, right? So you have 1 hex 0, which means you have a 4-bit shift to the left. 1 hex digit shift to the left. And in fact it's equivalent to hex FF rotated left by 4 positions. In this case, shift and rotate will be the same. So imagine the number we are looking at was, or is this, rotate left by 2 positions. Not 2, 4. So what will happen? What exactly is a rotate? A rotate is a circular shift. So when we are rotating to the left, this whole thing will go 1 position, 1 hex position, that is 4-bit position to the left. And this will come here. Yeah. So we are shifting left by 4 positions, 4 binary positions, which is equivalent to rotating left by 4 binary positions, or 1 hex position. Now ROL is not supported, only ROR can be supported, or ROR is only possibility here. So ROL by 4 positions is in fact ROR by 28 positions. Rotating something left by n position is equivalent to rotating right by 32 minus n position, and vice versa. Because rotation is an operation which preserves all the bits, so you can achieve the same rotation using either left rotation or right rotation. And in this particular case, we are constrained to use only right rotation. We don't have the possibility to specify left rotation. Why don't we have the possibility? Look at the number of bits we have available. The total number of bits that we have to encode whatever we want to encode is 12 bits, of which 8 bits are taken up for some number which is to be rotated. So you don't have any bits at all to specify what kind of rotation. So ARM instruction set architecture version 3 says that rotation will be a right rotation. It's implicit. And ideally, to rotate and achieve a 32-bit value, you should have a rotation amount which is 5-bit. For a 32-bit number, to specify the amount of rotation, you require 5 bits. Because the range of valid rotations is 0 to 31. If you rotate a number 32 times, you get back the original number, right? You cycle all the bits back to its original situation. So ideally, we should have had 5 bits to specify the amount of rotation. Unfortunately, we are left with only 4 bits. Out of the 12 bits, 8 bit is gone. So in the whole instruction, all we are left with is 4 bits. So ARM instruction set designers put in a constraint for that. Okay, you can rotate it only by an even amount. Okay, so instead of saying it can be anything between 0 and 31, it can be anything even between 0 and 31, which practically means between 0 and 30, because 31 is not even, right? And that requires only 4 bits. The 5th bit is implicitly 0. For an even number, the least significant bit is always 0. right? For a number which is divisible by 2 raised to n, the least significant n bits are zeros. And for an even number, since it's divisible by 2, the least significant 1 bit will be 0. So you actually need only 4 bits to specify which of the possibilities within 0 to 31 we are looking at, right? And that is a 4 bits here. And the 4 bit value here is 14 decimal or 1110 binary. Why is it so in this case? This is FF left shifted by 4, which is rotated left by 4, which is equivalent to it rotated right by 28. 32 minus 4. Correct? And rotate right by 28 means that the rotation amount is 28, which is encoded as 14. 28 divided by 2. The last bit is implicitly 0. You have only 4 bits, even though you originally required 5 bits, but the last bit is 0 because it's constrained to be even, so we are good to go. Yeah? So that's how DP immediate is encoded. And that also means that you cannot have any arbitrary 32-bit number encoded in this format. Only some 32-bit numbers follow this format, and only those numbers can be immediates or can be the constants that is specified in the instruction. So as an assembly language programmer, do you really have to do this yourself? Well, not really. You just need to write the 32-bit constant that you want, and if it can be encoded in this format, the assembler will do it for you. If it can't be, then the assembler will say that this is an invalid instruction, or the value that you are trying to encode cannot be encoded in this format. Yeah? Yep, so that's the idea. Let's move on. I will have a small quiz sometime later where you can test your knowledge of this particular slide. Now that is the encoding for immediate. Next, encoding for register type. For register type, the 12 bit is used, or 12 bit is encoded in this format. The last 4 bits encode the register. These 5 bits specify the shift amount. This will specify the type of shift, and this is fixed to be 0. Now, there are 4 types of shifts possible: logical shift left, logical shift right, arithmetic shift right, and rotate right. 0, 0, 0, 1, 1, 0, 1, 1. There is another type of shift that we had studied in the level 2 module, which is RRX, but that is available only in the newer versions of our instruction set. Okay, this particular one we are looking at had only 4 types of shift or rotate. So you can see that there is no ROL, and ROL is kind of unnecessary because you can easily achieve the effect of ROL using ROR. If you need to do ROL by n, you can simply do ROR by 32 minus n. And that's why there is no ROL. Okay? And any attempt to include something like ROL would have required us to have one additional bit, which we simply don't have. Yeah. Now SHMT5 is the amount of shift, which is called 5 bits, and as we discussed earlier, 5 bits is good enough to specify any amount of shift or rotate for 32-bit numbers, right? Because using 5 bits you can express between 0 to 31, and that's good enough. So let's see an example, or before that, let's look at how the instruction format will look like. It will look like OP, which is R sub etc., the operand, the operation, destination register, first source register, and this is your second source. And your second source is a register, shift type, and shift amount. An example would be ORR, R8, R1, R3, LSR2. So here is your source 2, or this is encoded as source 2. The operation performed is R8 gets the value of R1 odd with R3 shifted right by 2 positions. Because it's logical shift right. By the way, there are 2 types of shift right, arithmetic and logical. And I hope you remember the difference. In logical shift right, so let's say if the number is, okay, let's see a 4-bit example. When you do logical shift right, let's say by 2 positions, this will come here, this will come here, this will come here, and these voids are filled up using zeros, and that is logical shift right. In arithmetic shift right, these voids will be filled up using MSB's duplicator. So let's say if the number is 1100, if you are shifting right by 2 positions arithmetically, then okay, this will come here anyway, this will come here anyway, but these positions, vacant positions or voids, will be filled up using the original MSB duplicator as many times as required. And this will allow you to preserve the sign and maintain consistency in an arithmetic sense. Whereas the same number, if done using logical shift right, would have given you 0011. So generally, arithmetic shift right is supposed to be used when you are dealing with signed numbers. It's a matter of your interpretation, right? So let's say if you are looking at a 4-bit number 1100, whether it is signed or unsigned is something which you know, not something which the hardware knows, or even the assembler knows in any way. Okay, so it's your responsibility to make sure that you use the correct type of shift right. And if you are using ASR, you are essentially implying that the number you are dealing with is signed. Okay, whereas logical shift right is used for unsigned numbers or quantities which are not necessarily numbers. Like for example, if you are trying to move an LED around, the lit LED, like for example a chaser light, then you will be shifting the position from one to the next, right? And then you use logical shift, not arithmetic shift. Okay, because those LEDs do not signify a number. It's just LEDs, on or off. So arithmetic shift right is used only with signed numbers. In all other cases, you use logical shift right. Whereas for shifting left, there is no concept of arithmetic or logical. There is no distinction. Simply because when you are shifting left, you are throwing away the MSB anyway. If that causes a problem, too bad for you. Right? That's all. Basically, you are looking at a number which wouldn't fit into the given number of bits available. It's about as simple as that. So anyway, back here, this is the operation to be performed. By the way, in the next chapter, we will look at how to create or design circuitry which can do all these kinds of shift. Yeah, that's for next chapter. Now, the condition here is 1110 because there is no condition specified here. OP is 00, data processing type. CMD is 1100 because it's OR. SRC2 is a register, so I bit is 0. And now comes SRC2 encoding. And SRC2 for registered or register shifted immediate is this. Where SHMT5 is whatever you specify here, that's 2 here. SH, which is a shift type, is logical shift right, and logical shift right is 01. So you have 01 here, binary. This is decimal, by the way. So in binary it will be 00010. And RM is this register, which is R3, which is 0011. So that's how you encode SRC2. Yeah. Sorry? Oh, yes bit. S bit is 0 here because there is no S specified here. This is whether the flags are saved or not. Now the last one within DP is register shifted register, where this SRC2 field is encoded as this, where this is the register shifted by a type specified here and an amount specified in register RS. Example, EOR, R8, R9, R10, ROR, R12. So this is your source 2. Now this R10 goes here. So it's 10, so it will be 1010 binary. Shift type is ROR. ROR is 11. So it's 11 here. And RS is the amount of shift, which is R12. So R12 is 1100. So now you see, you are specifying the amount of shift in a register, not as an immediate. But a register has 32 bits. You don't really need all the 32 bits to specify the amount of shift of a 32-bit quantity. So only the least significant 5 bits from the register are in fact used. Right? The shift amount needs to be only within 5 bits, but the shift amount, since it is specified in the register, is 32-bit. So only the least significant 5 bits will actually be used. And that completes register type. Next is memory instruction format. So not register type, DP type, register as well as immediate. Now memory instruction format, and there are basically 2 types of memory instructions: load and store. Load is to move the data from memory to processor, loading a register with the content of a memory location. So that's LDR, load. Store is the opposite, storing the content of a register into a certain location in the memory. There are actually 4 variants: LDR, STR, LDRB, STRB. LDR and STR deals with one word at a time. So you are moving 32 bits of data in and out. So even when you specify a certain memory location, you are in fact accessing that location as well as the 3 subsequent locations. Because one location in the memory has only 8 bits. Memory conventionally are byte oriented. All commercially available memories are byte oriented. Every separate byte has a separate address. But one word, assuming word size is 32-bit, requires 4 locations to be accessed. So LDR and STR deals with 4 locations at a time, which is unnecessary when you are dealing with smaller chunks of data. Like for example, if you have declared something as a character, say character A, or if you are having a string, an array of characters, array of bytes, then you are dealing with 1 byte at a time, right? So dealing with or trying to fetch 4 bytes is unnecessary. And then we use LDRB instead of LDR. LDRB is a byte oriented version of LDR. Now let's look at the encoding. OP is 01 for memory type. The front field is fairly complicated. It's I bar PUBWL. We will see each of those later. Then we have RN, which is, now it's not fair to call it the first source operand because it's not an arithmetic or logical operation. It's a base register. So RN is your base register. RD, again not fair to call it a destination register. It's destination only for load and load byte. It is the data source for store instruction. For store instruction, RD is the register whose content will be sent to the memory. Yeah. So it is destination for load, it is data source for store. And then this part is the part where you specify some kind of an offset to the base value. The base value is specified in RB, offset is specified in SRC2. And there are two different ways you can specify the offset. The offset can be specified as an immediate, in which case it's a 12-bit immediate, or an immediate with a magnitude of 12 bits. The offset has a magnitude of 12 bits, or it can be specified in a register. And it's not just any register or register as such, it can be a register with an optional shift. By the way, when we have a register with an optional shift, sometimes we call it a scaled register. Because shifting in some sense is scaling by 2 raised to something, right? Either multiplying or dividing depending on the direction of shift. So you call it a scaled register. So anyway, here RM is the register which is subjected to a shift specified by this, the amount specified by this, and the type specified here. That's it. Now let's look at an example. STR R11 R5 minus 26. What type of an instruction is it? If you remember, there are 3 different types of memory instructions: pre-indexed, post-indexed, and offset type. Of which offset type is the simplest. It will look like this: LDR or STR R1 and inside bracket R24, where this is the base register and this is your offset. And both base and offset are written in square bracket. So the address location access this, or the memory location access this, whatever you have in R2, which is a 32-bit value, plus 4. R2 itself does not change, but the content of the location pointed to by R2 plus 4 goes into R1. Okay, sort of like R1 is equal to star of R2 plus 4. I said sort of because in C language when you add plus 4, you are not adding plus 4 memory location. It is plus 4 into the type of the data pointing to. Okay, but here let's avoid that complexity. But roughly this is what happens. But R2 itself does not change. Whereas there are these two variants, pre-indexed and post-indexed, where the base register itself is modified. So let's say if there is an instruction LDR R3, R5, 16 with an exclamation mark. The way memory access is done is very similar to the previous case. The memory location pointed to by R5 plus 16 is accessed. The content goes into R3, content of that address location. But R5 itself is modified to R5 plus 16, which did not happen earlier. And then there is post-indexed, where the bracket is simply around the base register. The so-called offset is written outside. So the memory which is pointed to by R1 is accessed. And then R1 is modified to be R1 plus 8. So the offset specified is not used in the current memory access. That's why you call it post-indexed. That index is used only for a post-processing, not for memory access itself. Now, these are distinguished using P and W values, which are these two bits, P bit and W bit here. When P is 1, it means that the offset is added to the base register before memory access. Or in other words, the offset is used in memory access. Now, W means write back, where whether the address used for memory access is written back to the base register or not. So for offset and pre-index mode, P is 1 because this is certainly used in memory access. But is the base register modified? Not for offset, yes for pre-index. Now for post-indexed, you might wonder why this is not 1, right? Because for post-index, the base register is actually modified. But we don't call it write back because write back by definition is writing back the address generated for memory into the base register. And here in post-index case, while R1 is modified, it's not modified to be the address used for memory access previously. Okay, so that's one argument or one way you can argue that, well, here it should be 0. Now that's PW, and 01 is obviously not supported because not doing pre-index and then writing back doesn't make sense. Because for write back, a prerequisite is that you should be doing a pre-index, right? Or adding the offset to the base value. And then there is L bit, which is 0 for STR, which is 1 for LDR. And then there is B bit, which is 0 for word oriented memory access, 1 for byte oriented memory access. So LDRB, STRB will have B bit as 1. Now, not a big difference. Here it is I bar, not I. Okay, so it is immediate when that bit is 0, which is opposite to how it is for data processing instructions. Okay, I don't have a good explanation for why it is so. Well, the designers of ARM, in whatever wisdom they had, decided that it has to be the other way around. Yeah? So yeah, I bar means immediate bar, which is 1 for register type, 0 for immediate type. And then there is U bit, which is odd. So if the offset that you are getting is supposed to be added to the base value, then U bit is 1. If the offset is supposed to be subtracted from the base value, then U bit is 0. Okay? So this offset is the magnitude of the, it's just the magnitude, the offset that is specified here. The sign of the offset, that is whether it is supposed to be subtracted or added, comes from the U bit. Okay, once again, this is just the magnitude of offset. Whether that magnitude is added or subtracted, which in some sense implies the sign, is in U bit. Now, we'll be clearer once we see an example. Here, the operation to be performed is the memory location pointed to by R5 gets the value of R11. So R11 is stored into the location pointed to by R5. It's a post-indexed instruction. The bracket is around R5. So this is not relevant for current memory access. This is used only to modify the base register. And the base register will be modified to be the current value minus 26. Decimal 26, because we don't have any hex 26, right? In the absence of any of this, it simply means decimal 26. Let's look at the encoding. It's unconditional. Even memory instructions can be conditional, but here it's unconditional, so 1110. OP is 1 because it's memory type. Func field is all 0. Why is it all 0? It's post index, so PW is 00. Your offset is specified as an immediate, so you have I bar equal to 0. Immediate, if it is immediate, it's 0. Then the magnitude is 26, and that 26 is encoded as an immediate word. Magnitude. Now, how is sign accommodated? You specify whether that magnitude is supposed to be added or subtracted, and here it's supposed to be subtracted. So u is equal to 0. If it was plus 26, it would have been 1. So in some sense, that u bit together with these bits is a sort of a sign and magnitude representation. Okay, but it follows the doesn't follow the convention. In conventional sign and magnitude representation, when the sign bit is 1, it's negative, sign bit is 0, is positive. Here it's the other way around. Okay, so they don't call it sign, they call it I. Okay, which is supposed to be 1 for addition, 0 for subtraction. So here it is, the offset is negative, so the magnitude of the offset is subtracted, so u is 0. And it's a byte it's not a byte oriented instruction, there is no strb, so b bit is 0. And it's not a load instruction, so load bit or L bit is 0. And that's it. Okay, so you can try it, you can write this instruction in Kale assembler, assemble it and see the binary equivalent or hexadecimal equivalent. You will be able to see that it is E405B018. Now another example for an offset specified in a register, STR R9, R1, R3, LSL2. The operation performed is the memory location specified by the base register R1 plus the offset which is specified as R3 shifted left by 2. So the overall memory address is computed and that location is written with the content of R9. So R9 is stored into the address specified as R1 plus R3 shifted left by 2. Now you may wonder why have all these complications, right? Well, it allows you to specify or traverse arrays of structures, etc. quite easily if these instructions are available. In a simpler instruction set like RISC-V, these kind of complications are not available. So you require multiple instructions to increment your pointer to traverse an array, whereas here it can be done in one shot. Yeah, so it is a bit CISC instruction, bit of a CISC instruction, or CISC-like instruction. So, well, your condition is 1110 unconditional, OP is 01 because it's memory type. Now, func field, I bar is 1 because it's register type. Then it is just an offset type, not pre or post index. So PW should be 10 based on the table we saw earlier. Okay, offset type PW is 10. Then there is no negative here, U is 1. There is no B, it's not STRB, so B is equal to 0. And it is a store, so it is equal to 0. Now, how about SH and AMT and SH? Logical shift left is 0, 0 here. So that field is 0, 0. Logical shift left. The amount of shift is 2. So it will be 0, 0, 0, 1, 0. And the register to be shifted is R3, so 0, 0, 1, 1. That's it. Now the last one, branch. Okay, which is done in a pretty interesting and slightly complicated manner in the real ARM processor. It encodes instructions B and BL. The first 4 fields or first 4 bits or the first field is the same. It is condition. Opcode for branch instruction is 10. And then the func field is 1L. So bit number 25 is hard-coded to be 1 for branch instructions. Bit number 24 is L bit. L is link. BL means branch with link. So for example, if I have a BL label and the label is here, so it does two things. Number one is it will store the return address, that is the address of the next instruction, into R14 link register, and it also changes your program counter to be whatever address you have corresponding to label, which is what we call the branch target address. So this label stands for an address, right? So your PC will change to that particular address abruptly. So here BL changes two registers, R14 and R15. Now the rest of the the rest of the bits are used as one single field called IMM24. IMM24 is the number of words branch target address is away from the current PC plus 8. In the newer versions of ARM, it's PC plus 4, but in the older versions, it's PC plus 8. Again, don't ask me why. I did not design this instruction set, and I tend to believe that it is a decision that they came to regret later, and that's why they changed it for newer versions. Yeah? Now, it will be clearer when we look at an example. So let's say you have a test label here, and the corresponding address is 8040. This is the address in the memory where this instruction is, and that address is specified or identified using just a label, test. And here is a branch instruction which, when the branch is taken, and here it's an unconditional branch, so it will be taken. So after this line, the execution jumps back to the line with the address 8040, which is LDRB R5 R0 R3, this one. Now, offset is computed not from PC, it's computed from PC plus 8. And if PC is this is the address of the current instruction, which is PC. PC plus 8 is the address of this instruction, which is 8058. Now, how many words away from PC plus 8 is your branch target address? You count back. 1, 1, 2, 3, 4, 5, 6. So how many words away is it? Minus 6 or negative 6. So what you encode here as a 24-bit value is minus 6. Now it kind of makes sense. Okay, 8058 is PC plus 8. This is your branch target address. So what is the offset? Branch target address minus PC plus 8. Okay, which is minus hex 18 bytes. And that is easy to see, right? 8058, 8040. So minus hex 18. Don't call it 18, it's not decimal, it's hexadecimal. Yeah, decimal, it's decimal 24. Because 18 is 16 plus 8, which is 24. And this many bytes, but we don't encode bytes, we encode words. So hex 18 bytes, or in decimal 24 bytes, is 6 words. 6 words backwards. So that's why you have minus 6 encoded here. Now, for a change, this number is encoded using 2's complement. So far we did not look at a 2's complement scenario, but here it's positive or negative, so it's signed, so it's encoded as 2's complement. So minus 6 plus 6 would be 0, 0, 0, 0, 1, 1, 0. Here you have 23 zeros followed by 1, 1, 0, right? 3 bits here. So minus 6 will be the 2's complement of this, So the 2's complement of a bunch of zeros followed by 1 1 0 is. Remember, there is this easy technique. Look for the first one from the right, draw a line there, write down everything, and complement everything to the left. So it will be this. So it's all ones followed by 1 0 1 0. The 2's complemented version of 0 0 0 0 1 1 0. That's it. Or you can flip all the bits and add one, but what I did was just an easy way of doing it. So yeah, that completes our brand instruction. And these are the instruction formats for your ARM version 3 processor. Okay, have a good look at it, and then we will put the various building blocks together to be able to execute this instruction set in the second part of the chapter. Which again is kind of similar to what you did for CG3208 if you have taken that module, but as you can see, there are significant differences. So we will do that after the break. So let's come back here by 7:40. Whatever you have in R11 is the data to be returned to the location, and the location is specified as R5 minus 6. R5 contains what's the secondary quantity? Minus 26 is the effective address. It's always positive. R5 contains the 32 quantity.
Into the PC. So PC is PC. Okay. Then you go run something.
X1.
How much number is 24?
Yeah, X1
is all 6 before. So it goes to minus 6. Oh, so it goes to 0 by 6. Then the offset is.
Or
Oh, yeah,
1 inch, right? 1 inch is 0 0 0 0 1 1 0 0 0. So this many bytes, but we want the number of words.
So I thought this is
we have is 1
minus. Oh,
because we are counting the number of words, right? So it's number of bytes divided by 4. And divided by 4 is just common of 2 zeros. You are in some sense shifting it to the right by 2 positions.
For my each row is over like
So dividing by 2 raised to n is knocking off insignificant n bits.
So
You shift it to the left, so you
this
put
one
that
is 18 by 3 because you add
So-
then you go back to 40.
Yeah, so if let's say you have a number x,
Then how
x into 2 raised to n is x shifted like x divided by 2 raised to n is x shifted right by n position, which is knocking off n least significant bits.
Oh, so it's 24 minus 18.
Yeah, and that is expected to be so because program counter will always point to locations which are
Oh, good.
which has last 2 bits.
So you plus 8 minus Because BTA is 1, 2, 4, 5. Oh, 18 is what 18. What damn it?
So when something is divided by 4, it can be divided by 4. If it can be divided by 4, it means the last 2 bits are always zeros. And then you don't waste bits.
Oh, yeah.
Oh my god. This value is our second operand, right? But how do you express your second operand? You're holding this value to play. So ARM has specified that this is to be represented in this format. Otherwise, well, if it is not representable in this format, you can't have it as a value second operand. So 8 plus 4 bits. If you had only 8 bits and if you are not allowed to use this, then you can only have 8-bit values. Here you are looking at a value which is more than, or a constant which is more than 8 bits. Strictly speaking, doesn't fit into 8 bits, right? Yeah. Then the ARM allows you to encode those constants which does not fit into 8 bits, provided they can be expressed as an 8-bit value rotated right by an even number. So any 32-bit value that can be expressed as an 8-bit value rotated right by an even number, then you can have it as a constant. Yes. Yeah, but not all 32-bit values. Like for example, if it was FF1, 2 by 40. If it is FF, it's okay. Sorry, 7 F's with 1 0 1. It can only be an 8-bit value with any number of zeros. So FF is an 8-bit value. 1 1 1 1 1 1 1. Then the rest has to be zeros and then from the back.
Also, it has to be zeros.
Yeah. Yeah, you could say that. it works. Sometimes it doesn't work. It's as simple as that. Because of course, if you don't have all the 32 bits available to encode a number, then you have to put in constraints or restrictions. Elaborated is a tool's first impression of how it will look like. Only after synthesis you will be able to know whether something is meaningfully storing value or not. So let's say if there is a value which has no effect on output, elaborate design will still show it, but synthesized version won't. You should look at it and see whether it's really it could be a problem. More likely a scenario where that value doesn't have to be yeah, could be because of that. Yeah. So once you are home, you got to see the code which is many times able to realize that these are going to be zeros and these. So no point in zeros. Yeah. So it will realize that those things are not very affected. So it will just generally, if you do a post-synthesis, if you are getting what you should get, that means that the tool was very smart to realize that, well, I was putting this one, it is not this. So it will not cause a functionality. Sometimes revival is very smart, sometimes because all these are based on heuristics. So sometimes it's your day, sometimes it's sometimes you make a small change and then it's going to optimize that. And later you realize that it's smart enough, you must realize that you are not using some of the finance because of the processor because you are not so you go all the way and to analyze how the memory is used by the processor, which is quite smart. Okay, welcome back. So some of you were asking about these words, bytes, etc. Now you can see that x18 bytes is 0000 whatever. Okay, 1000. So this is 18, right? X18 is 24 in decimal. So 24 bytes is 8 words. Sorry, 6 words. Because 24 divided by 4 is 6, right? So you can see that is essentially removing these two. Removing these two will give you 6. Dividing by 4 is essentially knocking off the last 2 bits. Because dividing by n is knocking off the last or least significant n bits. And here we are dividing by 4 to find the number of words. So 24 bytes or hex18 bytes is 6 words. And you can easily see that by knocking off the last 2 zeros. And why did ARM decide to knock off these 2 bits? Why are those 2 bits not encoded? That would mean that your offset cannot be something other than a multiple of 4, right? Is that really okay? Yeah, it's perfectly okay because we are talking about program counter. Program counter always points to addresses which are multiples of 4. Because whenever it increments or whenever it points to a valid instruction, it's looking at an instruction which is divisible by 4 because it always increments by 4. So the last 2 bits for the actual address will be zeros anyway. So naturally, offsets should also have last 2 bits 0. And if the last 2 bits are always going to be 0, why waste bits encoding obvious things? So by not encoding the last 2 bits which are zeros, you are able to have a range of offsets which is 4 times than what would have been possible if you had encoded a byte offset. Right? So what is the range of addresses that program counter can jump? What is the range of addresses? From PC plus 8, it can jump by an amount which is minus 2 raised to 25 to 2 raised to 25 minus 1. Why is it so? Sorry, this many words, not bytes. Yeah? Because you have 26 bits of offsets. So, 26 bits can accommodate in signed number system minus 2 raised to 25 to 2 raised to 25 minus 1. But this offset is a word offset, not a byte offset. So how many byte offsets, or what is the range of byte offsets, or what is the range of addresses? The range of byte offsets is the range of addresses, right? So the range of addresses is 2 raised to minus 2 raised to 27 to 2 raised to 27 minus 1, or minus 4 to be precise. Yeah? Here, right? You have 26 bits of offset for words. So in some sense almost 28 bits of offset for bytes. And using 28 bits, you can represent between minus 2 raised to 27 to 2 raised to 27 minus 1. It's minus 4 because we are looking only at multiples of 4. The last 2 bits are implicitly zeros. Okay? So yeah, with that, let's look at the microarchitecture, which is somewhat straightforward if you understood this much. We are not looking at the microarchitecture which executes all the instructions and all the variants that we have seen. That will be quite cumbersome for a start. What we do is to create a basic processor and then incrementally add support for various instructions and features. And that's precisely what you are going to do in the lab as well. In lab 2, you create a fairly basic processor, and over lab 3 and lab 4, you make the processor more and more capable, that is to be able to deal with more instructions and more variants of instructions. There are various ways in which you can design the processor, either a single cycle, multi-cycle or pipeline. We will start with single cycle and later we will make it pipeline. We won't look at multi-cycle because multi-cycle is used only for relatively very simple processors. Single cycle is not even used in practice. Most processors that we look at these days, okay, unless you are looking for extremely cheap processors, are all pipeline. Now, microarchitecture or a processor design can be broken up into 2 parts. You have your data path. As the name implies, it's a path through which data flows, which consists of data storage elements as well as data processing elements. Data processing elements such as arithmetic and logic unit, data storage elements such as registers, and then there are elements which control the flow of data like multiplexers. So all together you have data path. And you need to have somebody who gives the appropriate control signals to control the data path. Like for example, for arithmetic and logic unit, you need to specify what is the operation to be performed. Whenever you have a multiplexer, you need a select input to decide which of the inputs will be selected or passed to output, etc. So all those are done by your control unit. Now we will start with a subset of instructions. So our processor that we design will have only add, sub, and or instruction capability. With register or immediate SRC2, no shifts. So quite bare bones. Then only LDR STR and only with positive immediate offset. And only branch, not branch with link. So let's get started. Architectural state elements are elements which store information. You remember your state machines? In fact, there was a self-study part in chapter 2. I'm not sure how many of you have gone through it, but it's again an extension of or a revision of what you already had in your digital design module. State machines, right, which are a combination of next state or output generation circuitry, which is combinational, and then state memory, which is sequential. So for a processor is nothing but a state machine, a very, very complicated one, which has state memories, which are all the flip-flops and memories combined in the processor or in the system, which is your program counter. You have your instruction memory. You have register file which contains registers R0 to R14, not R15. Then you have your data memory which store data. Here it stores instructions. And then you have NH and CV flags. So altogether, you have a lot of registers and memory. So the state of the processor is the complete set of bits that are stored within all this. Any guess how many states a typical processor will have? even for a relatively simple processor, the number of states is slightly more than the number of atoms in the observable universe. Because you are looking at a fairly large number of bits, and 2 raised to that many bits is just an enormously huge quantity. Yeah. So yeah, you have 16 registers. So PC is typically not considered a part of the so-called register file. The other 15 registers are considered to be a part of your register file. And PC is a register, so it will have a new PC value and the current PC value. So at every clock edge, whatever you have here will be just transferred to the output of the PC. It's a standard register. Then you have your register file, which is nothing but a logical collection of the rest of the 15 registers. And a register file now, in its simple form, below here it will be 0011. And the corresponding contents, which are 32 bits, will be at the output of the register file. Now the register file can also store information or store one register value or store one value into a register, and that is specified at A3. The value to be written is WD3. So this is where it is supposed to be written, sorry, what is supposed to be written and where it is supposed to be written. And to answer the question of where, you need only 4 bits, one of the 16 registers. What is to be written? A 32-bit quantity, right? And you have instructions where no register is written for that particular instruction. Like for example, if I have RDQ, R1, R2, R3, and the condition EQ is not satisfied, that means no register gets returned. So you should have a mechanism to specify whether a particular register gets returned, and that's write enable. Now, whenever there is a write, you should also specify when that write happens. Because if you don't know when you are writing, you are not sure about what you are writing. Okay, so that when question is answered by clock. Okay, so you are writing at the edge of a clock if write enable is true to a location specified by A3, and the value to be written is whatever you give at WD3. Right, so those are the 4 pieces required for writing. Reading is much simpler. For reading something, you need to give only one value, which is a location to be read, and in this case, which is a register to be read. So which of the 16 registers are supposed to be read? So that's 4-bit value. Now data memory has an address, the location to be read or written. If it is a read, that's all we need. The read value will be made available here. But writing requires 4 pieces of information, right? Where or which location is to be written, what is to be written into that location, whether that location is written or not, because not you will not be writing in every cycle. For example, for data memory, only store instructions write, right? Store instructions write to data memory. So only for store, this write enable should be asserted. And when is it written? At the edge of the clock. And then we have status registers, which are 4 bits. And here again, there are supposed to be enables. We will see later. For simplicity, it wasn't specified also. Now for instruction memory, there is no need for any enable or clock, etc. because instruction memory is a read-only memory. You specify the address and you get the data in the same cycle without waiting for any clock. Yeah. So now let's see how the various pieces are connected together, starting with the fetch stage. And we will be showing all this for LDR instruction, because some of you might already know. LDR is that instruction which stresses your single cycle processor the most. Yeah, it exercises the maximum amount of hardware in the data path. So to fetch an instruction, you specify the address of the instruction. And at that address location, you get the instruction. Or the memory will give you the content of that address location, which is your instruction. And that instruction will be 32 bits, and we have already seen the format of that instruction. So bits 19 down to 16 of that instruction is the first register that we are going to read, which is a base register. And this is the base address. So you give the base register identifier. So for example, if it is, let's say R5, this will be 0101, and this will be the 32-bit content of register R5, which is your base value or base address. Now, what next? You have your 11 down to 0 bits, which gives you the offset, right? We are looking at the immediate offset mode. So the offset is specified as a 12-bit value, okay, which is either added or subtracted to the base value, but here we are assuming a positive immediate offset. So it's always added. We are not looking at the case of subtraction. So you have a 12-bit value going in here, which will be extended to 32 bits by adding 20 zeros in front. So how do you convert a 12-bit value to 32-bit? By adding 20 zeros in front. Should it always be zeros, or can it be, or should it be ones at some point, or in some cases? Can you zero extend? Let's say if you have a number like 1100, if you want to convert it to 8 bits, can you always just put zeros? Only if you know that it is unsigned. For signed numbers, putting zeros in front will change the whole meaning and sign. Right? So putting zeros in front is okay only if we are looking at unsigned quantities. Is this 12-bit value an unsigned quantity? The answer is yes. Okay, even though we talked about it being sign and magnitude, that 12 bits is just magnitude, and then it's positive. When we say magnitude, we are talking about positive, right? Any idea of sign comes in only with a separate bit. So this 12 bits itself is a magnitude, it is positive. So at least these 12 bits standalone is unsigned. So we can put zeros in front without any trouble, without really bothering about whether the offset is supposed to be positive or negative. Yeah? Now, that's what it does. And this extend unit, is it a complicated unit as of now? Putting zeros in front, does it require a lot of hardware? Not really. Out of the 32 bits you have, you are essentially taking these 12 bits and then connecting 0 for the rest of the 20 bits, and this is your 32-bit value. You have 20 bits which are wired to 0, okay, plus the rest of the 12 bits that come from the instruction itself, and that's your 32-bit value. And once you have these two, you can do the addition. And let's assume that our ALU can do 4 different operations: addition, subtraction, and OR. And let's assume that addition has a control signal 0, 0. Yeah? By the way, this is not really the same as the CMD that we used here, even though these 2-bit value is derived from the original 4-bit value. You could have given it directly to, not a big deal, but I am just following the design in the textbook, where since it is only 4-bit, they have given only 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1, and assume that addition is 0, 0. So here we are taking the base value and offset and adding them together. Why it is addition and not subtraction? here you need to do subtraction only for negative immediate offset. And for now, I am assuming that my processor supports only positive immediate offset. At some point later, when we want to incorporate negative immediate offset too, we just make the ALU control to do or to be corresponding to subtraction. That's all. The way you are extending it doesn't make a difference, doesn't change. Okay, because even for a negative offset, you assume that you are subtracting a positive quantity rather than adding it. So that quantity is always positive, and that's why we always do only zero extension. And then you get the result. Let's call it ALU result, which is our address. What are we trying to do now? We are trying to generate the address for the load instruction. The load instruction is supposed to send the address to the memory, and when the memory replies or responds with the data is supposed to go into a register. So that output from the memory is given to the data input of the register file, the right data input. And the location to be returned or the register to be returned is specified by RD. This field RD, which is bits 15 down to 12, is where it is supposed to be returned. And for writes to happen, reg write signal should be 1. Okay, then at the next clock edge, the value will get returned. And here it is assumed that reading instruction memory, reading data memory are all, or reading register file are all combinational operations. You specify what you want to read, and the memory or the register file or whatever gives you the data without waiting for a clock. So it's all combinational. But writing itself can never be fully combinational. Writing something is by definition a sequential thing, so it requires a clock edge. Okay? So the writing happens at the edge of the clock. Now, in parallel to all these, you also take the current program counter value, add 4 to it, and that becomes the next PC value. And that writing happens again at the edge of the clock. So the time at which the register file gets written with the result is the exact same time instant at which your program counter increments to point to the next instruction. And that means we are done with the current instruction, right? Now, that contains a microarchitecture which can do only load. Okay, and a processor which can do only load isn't interesting, so we have to enhance its capabilities. Now, your PC can be a source or a destination of an instruction. So, an instruction such as add R15, R1, R2 is perfectly legal in ARM. Also, an instruction such as, let's say, add R1, R2, R15 is perfectly legal in ARM. Which means your PC can be a source or a destination or even both of an instruction. Now, remember I had mentioned that the register file does not store PC. PC is a separate register which is not considered a part of your register file. It's a separate, logically at least, it's a separate register. Okay, not a part of the register collection or register file. Now, the register file is designed in such a way that it can take in the so-called PC value and pass it to output provided the instruction is accessing PC. Like for example, in this case, okay, let me just change it slightly. Add R15, R2, R1, R15, R2. In this case, in the instruction format, the RN field will be 1111, right? Because your operand is R15. And that means this is 1111. And if this is 1111, this is supposed to be PC value. but PC is not stored in the register file. So what the register file does is take the PC that is supplied at the input and pass it to output. And when R15 is used as an operand, the operand is actually not the current PC value, it's PC plus 8. Yep. For older versions it's PC plus 8, for newer versions it's PC plus 4. But yeah, here we are looking at an older version, so it's PC plus 8. PC plus 4 is already available. In order to get PC plus 8, you have to add another 4 to it. And this is your PC plus 8. And when the instruction specifies that one of the operands is R15, this PC plus 8 that is supplied at the register file input is straight away passed to the output. So instead of reading from something within the register file will just pass whatever is supplied as PC plus 8 to the output. Yep. Now that addresses our concern of using PC as a source operand. And this can be the case for the second one too. Like for example, if it is 1111, then whatever you give here will be passed to RD2, the second output. So PC is not stored within the register file, but if the register file recognizes that you are trying to access PC, it will take the PC value at its input and will just pass it over. That's the idea. Now how about PC as a destination register? How about PC as a destination? For example, this case, you should be able to write the result into PC. Earlier, our circuitry was designed such that the result is returned to register file. Now it's not returned to register file, instead it's returned to the PC register. That requires a multiplexer at the PC input. Because for normal instructions which do not write to PC, PC plus 4 is what is written to PC. But for instructions which write to PC, like for example this instruction, you have a multiplexer which will have its control signal asserted such that this result will be written directly to PC. So you require that multiplexing at the input of PC. And let's call that control signal PCSRC. PCSRC is asserted whenever you are supposed to write a value other than PC plus 4 into PC. That is, if PC is not incremented the natural way, you have to assert PCSRC. Now that takes care of PC being a source or a destination. Now let's look at STR. Okay, the counterpart of LDR, except that the data goes the other way. Right? The idea is to write RD into memory. So instead of loading RD from memory, we are writing RD to memory. So RD is a source operand for STR. So this RD, that is bits 15 down to 12, is used as a source operand. And the content of that location or that register is supposed to be returned to data memory. So you need to make a connection this way. So that the register RD or the content of the register RD can be returned to the data memory. Yep. And that's all that you need to do for STR. STR writes to data memory. So memwrite, which is a control signal that is to be asserted when data memory is written, has to be 1 for STR. For all other instructions, this control signal will be 0. Now next one, data processing instructions. Data processing instructions with immediate SRC2. And here we are considering an immediate without shift. So we are just considering an 8-bit immediate. So right now our processor does not have the capability to do that rotated or shifted immediate. Yeah. The immediate is of this format, right? You have an ROT and you have this 8-bit value. And here we are assuming that this ROT field is always 0. There is no rotation. So your immediate is just 8 bits. Yeah? Or the constant that you are supplying is just 8 bits. So now there is a small problem with the extension here. For memory instructions, it was a 12-bit value that needed to be extended. Here it's an 8-bit value that requires extension. So now your extend unit has to behave differently for DP, data processing immediate type instructions. So if it is supposed to give 2 different behaviors at 2 different times, it needs to be told what behavior is supposed to be exhibited. And that is done using a control signal called IMM-SRC, which is, let's say, 0 for DP immediate type, 1 for memory type. So when this bit is 0, it will take in 8 bits and add 24 zeros in front. When this bit is 1, it will take 12 bits and add 20 zeros in front. So 0 for DP immediate type, 1 for memory type. So the type of extension it does is now different. At the hardware level, how will it look like? Now we have 2 possibilities, right? So this extend immediate is either 24 zeros followed by bits, 7 down to 0 for DP immediate. Yeah, and 20 zeros followed by bits 11 down to 0 for memory type. So how will the hardware look like? Let's say you have 12 bits. So this is bit 0 to, let's say, bit 7, bit 8 all the way to bit 11. So this is bit 8. Okay, 8, 9, 10, 11. And then we have all these bits from the instruction which we won't use anyway, 12 to 31. So what it does is, these 7 bits, so 8 bits, bit 7 down to 0, all of them will be used directly from the instruction. Because for both it's common, right? And for bits 8 to 11, there is a distinction. So you require some kind of a multiplexing where it's either this or 0, 0, 0, 0. And these are all zeros. These are 20 zeros. Here you have 4 zeros, all these 4 bits, and this is your 4-bit value, which is the bits 8 to 11. So bits 8 to 11 either come from the instruction or it's all zeros. It comes from the instruction for memory instructions. It's all zeros for DP immediate type instructions. And the higher 20 bits are zeros anyway for both. And the lowermost 8 bits are directly from the instruction anyway for both types. That is for DP immediate as well as for memory instructions. Okay, so the extend unit is essentially now just a 4-bit 2 to 1 multiplexer. 2 to 1 multiplexer because it has 2 possibilities and each possibility is 4-bit. That's why we call it 4-bit 2 to 1 multiplexer. Okay, so now that takes care of the second source. The first source is from the register anyway. And now the ALU control is dependent on the type of operation that is to be performed. It could be addition, subtraction, and OR, right? So this varies. And ALU gives out ALU flags which may or may not be stored depending on the suffix yes, but we will see that part later. Now the output of the ALU is your result. which is to be stored to wherever it's supposed to be stored. So your result is now no longer coming from the memory. It comes from the output of ALU directly. It bypasses memory altogether. And that requires a multiplexer, and let's call that multiplexer control signal mem to rec, which will be 0 for data processing type instructions, which will be 1 for load instruction. Load instruction is the instruction where data flows this way. That is, output of memory becomes your result. Whereas for data processing instructions and practically all other instructions, the result is essentially the output of ALU. Yeah. So that's where you have this mem to rec multiplexer. Now next, data processing immediate type. Sorry, register type. Here we are considering register without shift. So the second operand is just the register content directly. So this is your register content, but we had to give the correct register to be read here. Earlier what was connected here at the second read port. So these are what we call read ports, and this is your write port. The second read port was supposed to be RD earlier, because store instruction had the second value read from RD. But now the second value is supposed to be read from RM, because for data processing immediate type, the second register to be read is RM, not RD. RM is instruction bits 3 down to 0. Whereas for STR it was RD, which is bits 15 down to 12. So now there is a conflict, and to resolve it, you require a multiplexer. And that multiplexer will pass RD for STR, it will pass RM for DP register type. Here again you require a multiplexer, because earlier or so far the input of ALU always came from the extended immediate. But now it comes from the second register that is read. So you require a multiplexer, because you have to resolve between those two possibilities, and let that multiplexer have a control signal ALU SRC. And for DP register type, this control signal is 0, which means the data flows this way, which is what is expected. And for all other instructions that we have seen so far, that is for store, load, as well as memory, as well as DP immediate type, it always came from here. So for all of those, ALU SRC is no. Yeah, and that completes all instructions except branch. Now for branch instruction, there is one register that is read, which is, for a branch instruction, what is the register that is read? R15. But do we specify R15 somewhere? You know, in earlier cases, like for example in this case, when R15 was used as an operand, it was explicitly specified. So some bits from the instruction had already specified that the register to be read is 1111. Whereas for a branch instruction, it's not explicitly mentioned anywhere, it is implicit. Right? So you have to tell the register file that your output is supposed to come from R15. So it's supposed to take and pass it here, this way. And to do this, the register file should have 1111 at its read port. And let's assume that it's through the first read port that we are taking out R15. Earlier you had connected Rn directly there. But now it's not specified as Rn. Rn is in fact bits 19 down to 16. Bits 19 down to 16 does not hold 1111 for branch instructions. Right? So you have to have 15 hard coded as one of the possible inputs to the read port. So you have 15 there. Because it's not explicitly specified, it's implicit. So you have to hard code it and then give the control signal in such a way that this will be passed if it is a branch instruction. So that implicitly the value that you are reading is R15. Now IMM SRC requires modifications, or the extend unit requires modification. So far what the extend unit did was a 0 extension of either a 12-bit value or an 8-bit value, which doesn't work anymore, because for branch instruction, how do you compute the byte offset that is to be added to PC plus 8? The byte offset is the sign extended 24-bit immediate shifted left by 2. Why is it so? Because immediate 24 is a signed quantity which specifies the word offset. Okay, and it's only 24 bits, so to have the full number of bits, you need to do sign extension. Why sign extension? Because it's signed. Okay, unlike the cases so far where the offset value was considered unsigned, right? I mean, not including the U bit or whatever, but the offset itself or the magnitude itself was considered or was unsigned. But now it is signed, so you have to do sign extension, not 0 extension. Yep. And you had to shift it left by 2 because the offset that you had encoded was a word offset, but eventually we need an address which is based on byte offsets. So you have to shift it left by 2. So earlier you had that -6 encoded, right? So that -6 in some sense in that example had to be converted to -24 before doing the actual address computation or branch target address computation. So that's why you have this left shift, because you had done an implicit right shift there, and this left shift is to undo that. Why did you do, or how did you do right shift? Remember, it was like 1 1 0 0 0 like this, right? 1 8 x 1 8. How did you knock off these two zeros? By shifting to the right. Now to get the byte offset, you have to undo what you did. In other words, the hardware has to undo the shifting done by the assembler. The assembler shifted it right and encoded it. Now the hardware has to shift it left to sort of decode and extract out the byte offset. And that's why you have shift left by 2. Now how will the hardware look like? Things are a bit more complicated now. Here you have these bits 0 to 23 from the instruction, right? So how will the 32-bit value look like? You have to shift it left by 2. Do you need a shifter hardware for it? Not really. Shifting it by a fixed amount does not require any hardware. It's just appropriate wiring. So now your bit 0 becomes bit 2 of the result or shifted value. These two bits, bits 1 and 0, are grounded or 0. Because shifting left by 2 position essentially is inserting 2 zeros to the right. And now your bit 1 becomes bit 3 here and so on. Bit 23 becomes bit 25 here. How about bits 26 to 31? It's a sign extension, right? Sign extension is just MSB duplication. So it is the same thing. Same bit 25 used all the way to 26, 27, all the way to 31. That's it. But now this is different from the extension done for the previous two cases. So you require a multiplexing, and that multiplexing is again a part of the extend unit. And in order to control that multiplexer, you require control signals. Now the multiplexer, or now the extend unit, has to do one of the three different things. Either 0 extend the 8-bit value, that is for DP immediate, or 0 extend the 12-bit value for for memory instructions, or sign extend and shift the 24-bit value for branch instruction. So three possibilities, and that's why your immediate SRC control signal now need to be 2 bits. To specify one of the three possibilities, you require 2 bits at least, right? So we have a 2-bit value here. Now your immediate SRC does one of the three things, or it controls one of the three types of extensions. 24 zeros followed by the least significant 8 bits of the instruction to 0 extend immediate 8, which is for DP immediate, or 0 extend immediate 12 by putting 20 zeros in front for memory instructions, or sign extend and shift the 24-bit immediate for branch instruction. One of the three possibilities. And that's it. And that completes our data path. Now we have to look at the control unit design. So far we have been using all these control signals, so we have to design the control unit which generates all these control signals. So let us look at it one by one. But before that, the control unit can be thought of as having two different parts: a decoder and a conditional logic. All the signals that affect the state of the processor has to pass through conditional logic. So what are the signals which control the state of the processor? Mem write, rec write, PC source, and there is this new thing called flag write. Because these are the 4 signals which change the value of any register or memory, which essentially changes the state of the processor. Yeah? Okay, of course, every instruction changes the state of the processor by changing PC, but I am talking about scenarios other than incrementing PC by 4. So, for doing anything other than incrementing PC by 4, you have to activate one of these 4 signals. And that is done only when the condition specified in the instruction is true. So, you need to do a condition check. So, to do condition check, you need to know what are the flags, that are stored in CV, which are considered to be stored inside the conditional logic. What is a condition specified in the instruction? So for example, if it is EQ, then this is 0000. The first 4 bits of the instruction is a condition under which that instruction is executed, right? So that comes from the instruction. Initial CV flags are stored inside the condition logic. And to store something, you require a clock, and that's why conditional logic is a sequential circuit. And to store the flags, you need to specify or give the flags. That's ALU flags. Where do the flags come from? The arithmetic and logic unit. So, as a result of the arithmetic or logic operation, the ALU will give the NSXCV flags. They are stored inside the conditional logic if the suffix S is specified. So you have to condition this and then pass it to the data path as PC, SRC, reg write, mem write. So these are, I would say, prospective PC, SRC, prospective reg write, prospective mem write. And there is also flag write, which is not given to the data path because that is to control whether the flags are written or not. And the flags are inside the conditional logic itself. So it's not given to the data path. Yeah. And then the decoder, which only gives signals which channel data directly to the data path. All the signals which control writing, etc., are passed through conditional logic. Whereas those which are purely for channeling data are given directly to the data path. Like mem to reg, ALU SRC, in IMM SRC, reg SRC, ALU control, etc. Right? They are sent directly. Now, if you have an instruction like RDQ, and if the condition EQ is not true, all these will be zeros. Now, PCSRC and memWrite were supposed to be 0 anyway for an add instruction. But normally for an add instruction, regwrite is 1. Because add instruction will write to a register. But it will be zeroed out by the conditional logic if the condition specified is not true. Now, flag write is something which we did not really talk about so far. And flag write is slightly complicated for the ARM processor because not all instructions with suffix s control all the flags or write all the flags. Like for example, an instruction like RDES affects all 4 flags. Whereas if it is something like ANDES, it doesn't affect some of the flags. It affects only N flag and Z flag. C and V are not affected by AND instruction. Because C and V are arithmetic related. Logical instructions do not really have any influence on C and V. C and V do not mean anything for logical instructions, like AND. It's only for arithmetic instructions like add sub. So CV are not affected by ANDES. But here again, there is a slight complication which we will see later. You will try it out in the lab. But for now, just assume that C and V are not affected. Okay. In reality, when there is shift which is non-zero, C is affected by the last shifted bit. For logical instructions too. But for now, let's assume that C and V are not affected by logical instructions. So, N and Z flags are saved by all instructions with suffix s. C and V are saved only by arithmetic instructions, not by logical instructions. So, we need to have 2 separate bits for the enable for flags, for the flag registers. So I call it flag W1 and flag W0. Flag W1 is 1 for saving NZ. So all instructions with suffix S will assert flag W with number 1. CV is asserted only by arithmetic instructions with suffix S. Logical instructions will not assert flag W0 because C and V are not supposed to be modified by logical instructions. Yeah. Now, with this knowledge, let's look at the decoder. The decoder, I am just following the textbook, is split into 3 parts: the PC logic, the main decoder, and the ALU decoder. The main decoder takes in the opcode, also looks at the func field, and will generate reg W, mem W, mem to reg, ALU SRC, IMM SRC, reg SRC. And if it is an operation which involves ALU, a DP instruction, it asserts ALU OP to the ALU decoder. It's just an internal signal between the 2 blocks within the control unit or decoder. And if it is a branch instruction or an instruction which writes to R15, then the branch signal is asserted. Okay, again, which is purely internal within our decoder. Now let us design it one by one. The main decoder. Okay, you have OP. OP00 means it's a DP instruction. And for a DP instruction, you look at func5, which is the I bit to decide whether it is DP register or DP immediate. Yeah. And then we have memory type instruction, where you distinguish whether it is load or store by looking at bit number 0 of the func field, which is the L bit. We don't look at func5, which is the I bar bit, because we are assuming for now that we support only immediate offset, not register offset. If our processor supports register offset, this bit should have been looked at, but now we don't look at it. Yeah? Remember, we are doing things incrementally. Later on we will look at it, but for now, no. And for branch instruction, all we care about is that, well, the instruction is a branch instruction which is based on OP being 10. So now we know which category of instruction it is. And depending on the category, we can figure out what are the various control signals. So branch control signal is asserted, or this is asserted only for branch instruction. So for all other instructions, it's 0. Yeah? Now let us look at mem to rec. Mem to rec is asserted when the data is supposed to flow this way, which is the case only for load instruction. For all other instructions, the data flow this way. Data flows this way. But there is one instruction for which the data doesn't really meaningfully flow at all, which is STR. For STR instruction, everything stops here. There is no result to be returned to register file or PC or wherever. Right? It writes to the data memory and it ends there. So for a store instruction, it doesn't really matter whether you are passing this or this. It doesn't mean nothing gets passed. One of the two has to. But for store instruction, we don't care what gets passed, because the value here will not end up getting written anywhere anyway. So it doesn't matter what you pass, because nothing gets stored eventually. Right? I mean, nothing gets stored into register file or PC. I mean, PC will store the subsequent instruction or the address of the subsequent instruction, but nothing significant, nothing different. So you can see for load instruction, mem to rec is 1. For store instruction, it's a don't care. For all other instruction, it is 0, because the data is supposed to flow this way. Now how about memw? Only instruction that writes to memory is your store instruction. So for store instruction it's 1, for all other instructions it's 0. Can I say for all other instructions it's don't care? No. It has to be 0, because memory should not be written for other instructions. Yeah? I mean, don't assume that there is nothing at the memory input at all. See, there is something here and something here all the time. Right? In digital circuits, there is no scenario called nothing is there. There is always something. It's a question of whether you are making use of that something or not. You make use of that something only when it is relevant for you. But even otherwise, there is something here. So for all other instructions, we deassert write enable so that nothing gets written. Yeah? Even though there are values here which are not relevant for us. Then how about ALU-SRC? ALU-SRC is the signal that controls whether this or this goes as a second input of the ALU. And only for DP register type instruction, data flows this way. For all other instructions, the second operand comes from extended immediate. So for DP register type, it is 0. For all others, it's 1. Okay, and so on and so forth. Okay, I am not going to bother about these two columns. I leave it as an exercise for you to figure out, which is quite straightforward. Then, how about ALUOP? ALUOP is 1 for data processing type, 0 for all others, and it is an indication from main decoder to the ALU decoder that it's a data processing instruction. Now let us look at the ALU decoder. ALU decoder will get ALUOP equal to 0 for non-DP instructions, and it is 1 for DP instructions. And for non-DP instructions, the ALU always does addition. Why is it so? What are the non-DP instructions that we are talking about? Memory type, and we assume positive immediate offset, so it's always R. And for branch, offset can be positive or negative, but it is signed, so you are simply adding that offset, which can be positive or negative, so it's still addition. So it's always 0, 0. And flag right is 0, 0 for non-DP instructions for sure. And if it is a DP instruction, you look at the func field to decide what type of operation it is and give the appropriate control signal to the ALU. And we look at the S bit to decide the flag right bit. If S bit is 0, flag right is always 0, 0. If S bit is 1, flag right is 1, 1 for add and sub. Why is it so? Because add and sub instructions affect all the flags. Whereas for and or instruction, it is 1, 0 because only NZ is affected, CV is not affected. Yeah? Now the last part of the puzzle here is PC logic. PC logic is what are the inputs to the PC logic? Indication of whether the instruction is a branch instruction, and also read W. And there is also this input RD 3 down to 0. Why do we have this? Because PCS is to be asserted when the instruction is a branch or when it is a non-branch instruction with destination R15. So for example, R15, R1, R2, that should also assert PCS, correct? So that's why we have to know whether your destination is R15 or not. So if it is a branch instruction or if it is another instruction with destination R15, then PCS has to be asserted. But not every instruction with destination R15 needs to assert PCS. Why? What if it is STR R15 something? Should it assert PCS? In this case, RD is R15. It should not assert PCS because for a store instruction, R15 is a source, not a destination. So you have to guard against store instruction modifying PCS, and that's why you require a rect W. So here you see PCS is whether RD is R15 and rect W. This is to filter out the possibility of STR instruction spuriously affecting PCS. Or when the instruction is branch, then PCS is asserted. And if the instruction is executed, that is when the condition is true, PCSRC is PCS. or PCS is passed directly to this multiplexer. Whereas if the instruction is not supposed to be executed, that is, condition is not true, like for example, if it is BEQ but EQ is not true, or when it is, you know, add R15 something, sorry, add EQ, but EQ is not true, then PCSRC should be zeroed out. So PC will increment normally to PC plus 4. So that completes PC logic and that completes this part. Okay, now with conditional logic, we have completed, or once we do conditional logic, we will be done with this microarchitecture, which we will do in the next class. And some of you had asked regarding, you know, lab 1, the frequency to be maintained, etc. If you notice very carefully within lab 1, it's mentioned that the 1 Hertz frequency mentioned is just approximate. You don't have to follow it exactly. Okay, and then when the button is pressed, it's supposed to be 4 times the frequency whatever you had originally. Yeah, and I had suggested using 2 raised to 24 and 2 raised to 26. If it is 2 raised to 26, you know, 100 megahertz divided by 2 raised to 26. 2 raised to 26 is 100 megahertz is, you know, 100 into 10 raised to 6. 2 raised to 26 is 1024 into 1024 into 64. And you can see this is approximately 1.5. Okay, 1.5 Hertz effective frequency. And since you are supposed to show 2 halves, the frequency of instruction display becomes half of this. So that becomes about 0.75. Okay, which is perfectly okay. By the way, for those who are interested, looking at all the 26 bits to determine whether you are looking at 2 raised to 26 minus 1 is actually quite inefficient. Okay, there is a much better way to do it rather than or without having to use a 26-bit combinational circuit. I am not going to give you the answer. Think about how it can be done. Okay? You can do it with just 1 additional flip-flop and 1 additional logic gate instead of using a 26-bit combinational circuit. Think about it. Think about how you can do it. Okay, so see you all next week.
Like, you just do shifting.